Okay, we are recording now. Well, hello everyone, and welcome to the Gaia Education Localizers webinar series. My name is Giovanni Charlo. I am the e-learning coordinator at Gaia Education. Today, I'm very excited to bring you this webinar entitled, How Can Black Holes Shake Our Worldview? With astronomer and Gaia Education webmaster, Pedro Pedrosa. This Glocalizer webinar is offered by Gaia Education to build capacity in systems thinking and holistic design for sustainability. Some housekeeping tips while we do the webinar. Please remember that this webinar will be recorded and will be later made available on our YouTube channel. It is also being broadcast on Facebook in our Gaia Education pages. Your microphone and video will be turned off during the webinar, but you are invited to post questions at any time in the question and answer box that it's in the Zoom application. Pedro will answer as many of these as possible at the end of his presentation. You can also post comments to share with other webinar viewers in the chat box in your Zoom application. So there is a way there for you to interact a bit with Pedro and with other people in the webinar. I want to see if I can advance this. Yes, good. I also want to point out other resources that Gaia Education makes available on our website, and that there is a 10% discount for these products for those on this webinar. Use the coupon code that you see up there, LiveWeb2019, if you wish to take advantage of the discount for our books, especially the Eco-Villages Around the World, which was just published last year with wonderful pictures and stories of eco-villages all around the world. And the 4 keys, which are the basis of Gaia Education's curriculum, especially the online courses. We also have a series of flashcards to initiate conversations in your communities about the Sustainable Development Goals. So these are Sustainable Development flashcards that you can use with your community to explore. Those are all 10% discounted. And along with that, there is a multipliers handbook that gives you step-by-step guide on how to use the Sustainable Development Goals flashcards. In addition, we have a number of courses running online. At the moment, we are just finishing the economic design course. These are all our Gaia Education Design for Sustainability online learning 10-month-long courses that lead to a certificate of designer for sustainability. At the moment, we are taking registrations for the Worldview design, which will start on May 20th in English and will be followed on May 27th by a Spanish version of the same course. We also have courses in Portuguese running at the moment. We are starting next week the economic design course in Portuguese. You can also follow us, join the community around the world that follows Gaia Education and engages in conversation about design for sustainability in many languages. So please visit our social media channels to join those communities. And while you're there, don't forget to subscribe to our newsletter and follow us on other social media. Today, I also want to mention our learning journey, which is a way to become a certified trainer with Gaia Education. And that journey involves taking a face-to-face EDE course, Eco-Village Design Education, EDE, then also taking a TOT, a Training of Trainers course. It's a 1-week-long workshop, and finally taking at least one of the dimensions of our online courses. After those 3 courses, you will then qualify to be interviewed to join our roster of Gaia Education certified trainers. There is no particular order to how those 3 courses should be taken. So if you've taken one of them, you are already on your way in this journey. So today's webinar, I have a great honor to introduce my colleague, Pedro Pedrosa. Pedro worked in the Astrophysics Center at the University of Porto in Portugal as an outreach officer for more than 10 years and as a research worker in areas related to cosmology, more specifically in the cosmological variation of fundamental constants and in finding optimal observational strategies for future telescopes. This promises to be a very exciting and very interesting webinar. So welcome, my dear friend, Pedro Pedrosa. I will stop sharing my slides so you can start your webinar.
Thank you very much, Gio. So let's start. I promise it will be a very short webinar because I know that our attention span is not that long. And another promise that I will make to everybody is that I will not put complex formulas and complex mathematical concepts here. So it will be very simple and very short talk with all of us. So if you have any questions, feel free to post during my talk. Don't have a problem with that. And I will try to answer as long as I go in my webinar. So to start a little bit about black holes. When I say black holes, we will go to the technology that we use to find this last picture of this black hole. But not only black holes, the astronomy itself, the astronomy as a whole has impact on mankind in our daily life that I will try to show you this. And this is the connection to the worldview, that is the conception of the world that we have, the cultural conception of the world that we have. So, and this is the connection that I will try to find during this webinar with the things that we find in astronomy and our land, our life in our land. So I will just do a quick summary of what I will talk about. I will do a historical context, not a very demanding one, but a very small one, very short one. Then we will talk about when the modern astronomy started. Then we go to two persons that are very important for this black hole talk, that is Albert Einstein and then Stephen Hawking. And then I will talk a little bit about black holes and then the modern instruments. That is the connection, or maybe the most obvious connection that we have with astronomy. So, the historical context. As many of you may know, this Stone Age, and this is home for a lot of rituals and a lot of interpretations that mankind did about the phenomena in the space. And for example, this one is connection with the rituals, but we also have a connection with astronomy, for example, in the seasons of the year, in agriculture, for example, or even in the tides. In the tides, there is a very close connection with the moon, and this is very important for fishermen, for agriculture, and all of that, and the eclipses, for example, also. We also have this mainly connected with the rituals. But as you can see, this is just a few images that can show us this connection with the space, with what is beyond our borders and our life here on Earth. You see the Muslims, they, in this bottom right picture, that they have a huge impact in astronomy. They found so many things. We also have the Maya culture, where they worship, they celebrate these eclipses, for example. And we have, for example, also a very modern ritual in the Freemasons, that they celebrate light and the moon and also the eclipse. So we can see that this connection between what happens in space, what happens outside our land, is a connection from more than 4,000 feet, 5,000 years ago until now. We still preserve this. Even, for example, the Easter. What is the day that we choose to be the Eastern Day? Is the first Sunday after the first full moon, after the equinox. So equinox of spring. So this is here in the North Hemisphere. So as you can see, astronomy and the space are in our lives daily. Now let's go a little bit about the modern astronomy. When the modern astronomy started, the modern astronomy started with this man that is Galileo Galileo, specifically with this book, Siderius Nuncius. That is, I will enunciate these books in the end in the bibliography that I did, but just a small, I will not talk about the book, but I will talk about the man and what he did. What he did, he was the first person to use a telescope to try to understand what is in the space. And he did this in the very difficult times, and it was to do science that will contradict religion, to do science that will contradict the common sense. It was punished by law. So it was very difficult times for science, but it was also very important that he did it. So using the telescope, he was the first person to observe the moons of Jupiter, the 4 Galilean moons, 400 years ago. And what are the 4 Galilean moons? Ganymedes, Io, Europe, and Callisto. This is the 4 Galilean moons that he discovered. And while he was observing this moon, he realized that these were objects going around and around another planet. So this was the starting point for him to draw the solar system as we know in our days, with the sun in the center, with the Earth going around the sun, orbiting the sun, and the moon also orbiting the Earth. And this was the first step to understand the solar system as we know in our days. And he used a telescope, and he also had a very funny story that is about Saturn. When he was observing Jupiter moons, when he was drawing this new concept of the solar system, the Inquisition was on him. So he was in house arrest, and while he was in house arrest, he continues observing the space, he continues observing what he might think that was planets, and then he starts observing Saturn, for example. And when he was observing Saturn, as you know, Saturn has a ring that is very visible from here with a small telescope like he had, and he saw the ring, and it didn't look like a ring, because sometimes I will try to draw because this is a little bit funny. Let me just stop sharing and I will draw what he observed. So when you are observing, he was observing it like this, the planet and the rings, but the rings can oscillate, we can see the rings like this, that is normal, but we can also see the rings like this, very close here to the equator of the planet, but very aligned with our sight of vision. So what happened is he thought it was a planet with ears. So he was ashamed of this discovery, and he told for himself, oh, if I tell anybody that this is a planet with ears, I will go to the fire right away. So he kept this for himself. He drew this on his notes, and he never told anybody. Just a few years later, when we were studying his annotations, then we realized that he was the first person, in fact, observing Saturn. But to continue, now we go to Einstein. Einstein, I just pointed out these 3 big theories that he had. One of them is the photoelectric effect. Is the one that maybe is more related to our daily life. The photoelectric effect, it means that when photons can reach a metal plate, it can have a reaction that will transform that in energy. And we use this in solar panels, we use this daily. So this was, not a lot of people know this, because usually people don't go to find the reasons why people win the Nobel Prize, but the photoelectric effect, it was in fact why Einstein won the Nobel Prize. He won the Nobel Prize by this discovery, by this article. But uh, later, it was a very amazing year when he has four amazing articles that was called, it was in 1905, that is called Annus Mirabilis. And two of these articles was the photoelectric effect and the special relativity. And when he was accepting the Nobel Prize, he didn't spoke about the photoelectric effect. He went there and he gave a talk about the special relativity that has nothing to do why he won the Nobel Prize. But this special relativity is very important for us to understand the black holes, because it's the first time that someone says that it's impossible to reach a velocity higher than the speed of light. And this is a very crucial moment in science when he says this, because this will help him to shape the entire general relativity. This will help him basically to constrain what he thought it was our space-time relation. So let's just stop here by this moment with this concept of the nothing can travel in a speed higher than the speed of light, and then we will back to it. But let's speak a little bit also about the Stephen Hawking. The Stephen Hawking, he postulated this Hawking radiation, that is a kind of radiation that black holes can emit. And I won't talk a little much more about this, but this is important to understand what is a black hole and how it forms and what is in fact a black hole in reality. So what we see is a singularity. A singularity is something strange in gravity. I will explain what it is, but I will explain what happens in gravity. But a singularity is something that is provoking everything, that is causing everything that is around. So because we have this singularity, we have this event horizon, and the event horizon is a cross line that everything that is inside the event horizon will never be able to come out. The gravity is so strong, but so strong inside, that not even light can come out of it. So this is, but the radiation of Hawking is something like this. When we have a phenomenon occurring right next to the event horizon, with the particle and the antiparticle, it can irradiate. We can see it. We can see some radiation coming from this part, but it's not like a black hole radiation, but we can see that black holes are losing matter when things are happening in the event of horizons. It's not, this is the edge, of course, but this is what is outside this line, can travel almost freely, not freely, because this is the next image that I will show you. So the horizon, the event of horizons, here is a black hole, and you can see a particle of light in the first image on the top. You can see this particle of light, and you can see that the light can travel anywhere. The light can go anywhere here. But as long as it's getting closer to the event horizon, you can see that the light cannot travel anywhere. The light are being conditional to this gravity coming from the black hole. But when it's inside, see that it's impossible to go out. When it's inside, the particle, the light particle, will always be pushed to the center of the black hole. Why this is happening? This is happening for a very simple reason. That is, I need to delete the, sorry. a very simple reason, that is the that is this formula. This formula is the Schwarzschild radius, and what it says, you know, when we want to expel a rocket from here, when we want to send a rocket to the moon or to the space anyway, what will happen? We will need to reach a certain amount of velocity for this rocket to be able to get out of our planet gravity. And this velocity is called the escape velocity. And just imagine, if our gravity, if our planet is bigger, has more mass, what we will need to put more fuel in the rocket so the rocket can reach this escape velocity. So as bigger, as massive as our planet is, the more velocity we need. But there is also another thing. Imagine, the gravity is not just about the mass of our planet. The gravity is also about the volume that the mass of our planet are occupying. Because if our planet has a certain dimension, but now imagine the same mass in a smaller planet, what will happen is that the gravity will increase also. Because what is important here is the density of mass. So the less volume, the same mass, the density will get higher. So what will happen here is that we will need a higher velocity also. So just imagine this, we have such a big planet that the only way, such a massive planet, that the only way for us to get out of it is to travel almost to the speed of light, okay? But that it's allowed by the special relativity. But now imagine that if the planet is so massive that to get out of it, you need to have a velocity higher than the speed of light. So this is impossible. According to the theory of Einstein, this is impossible to reach. So what we need to, how do we find this calculation? This is very easy. This is the radius that we want to escape from a certain planet, and this is the velocity. And here I changed it for the, I'm not sure if you're able to see when I point, but this is the velocity. But I changed it for c. C, the speed of light, is this number here. And this is the radius that we want to go, the radius that we want to escape. And this is this g, the constant of gravitation number is this one. So what will happen, basically, with a very simple rounding method, we will have this, the Schwarzschild radius, that is the radius that will limit the event horizon. So the radius that when everything is summed in that radius, it will not be able to escape. When it's outside, it can escape. Is the mass that we have plus this value here. That is this one divided by the, is this one divided by the speed of light. So as you can see, this value, we can change it. For example, if we have our planet, we put here the mass of our planet, and we will have the size of which our planet should be for it to become a black hole. Or we can change to the mass of the moon, or we can change to the mass of the sun. That's what we will see in the next slide. Which mass, here it is. Which mass should these objects in space should have to become a black hole? For example, in our planet, to become a black hole, maintaining the same mass, so to increase its gravity so much that it will become a black hole, it needs to be more or less 1 centimeter. That is a marble, a small marble. So if we have a marble that has the same mass as our planet, it will become a black hole. Every single particle of light that is inside that marble will become a black hole. And the sun, we can see it here. This is in meters, so the sun, it will be around 2 kilometers, 3 kilometers. So let's move. So this is the picture that we found about this new black hole. This is of course, we had pictures of black holes, but not directly pictures. So, and to take this, we use an instrument that I will talk later, that is an Event Horizon Telescope. But this is amazing. So the black hole is just that part inside, and you can tell me for sure what is the horizon event. Is this one? Is this line here? This line here, I'm not sure. I need to annotate, right? This line here is the event horizons of this black hole. So this is what is happening around here, is that light is rotating, or it's creating a halo of light that eventually this light will go in the black hole, because maybe it's rotating and rotating in this kind of form that will go in the black hole. And when go in, the black hole will increase its mass, will increase its size, and become more and more powerful, because this mass needs to go to somewhere. And what happens to a black hole, we don't know about it yet. What happens when something enters, where it goes, the mass. But we know that as much mass as the black hole congregate, what will happen is that it will become bigger and stronger. But this also explains one thing, that for us, just imagine that we want to enter a black hole. So we are here. This is our head, our arms, here our legs. So this is the gravity that we are feeling here is different than the gravity that we are feeling here. This is pretty obvious. Of course, in our planet, it also happens, but the difference is so small. But when we are closer to the black hole, for example, here, when we are closer to the black hole, the difference between our legs and between our feet will increase drastically. So the acceleration of the feet with the acceleration of the velocity of the feet and the velocity of the air will be very, very different, because this is what happens to acceleration. Imagine the acceleration here has a value 1, here has a value 2, but here has a value 3, but here has a value 4. This is an exponential growth. So what will happen to this person, for him, is that he will start stretching. So when he is closer to the black hole, he will be like this, bigger. And when he's right inside of the event horizon, he will be almost just like a line. You will be just a line of atoms, because the difference of acceleration, so the difference of velocity in the end, is so big from the first particle of him to the last particle of him, that you will become a line. So as you can see at some movies, this doesn't happen and people are able to enter the black holes, but this is not the reality. We are not able to enter the black hole. We are not able to enter as we are the black hole. Maybe something will happen inside the black hole, maybe it will change our perspective of things, but we are not able to enter and keep and be alive. So the modern instruments. So this is the relations that we will do. I'm not sure if I am being clear or not, but you can pose questions later. But this is the relation that I will try to do between astronomy, between black holes, and between our lives. Just for you to know, I study in Portugal, I live in Portugal, and here we don't have a space agency. We are just creating one, a very small one, in one island, in Azores. And why are we creating this? Because this is important for economy. To have a space agent is really important for economy. We work with the European Space Agency, and we work with the European Southern Observatory, ESO. We are part of these two consortia, and the Portuguese academic community, of course, and the country and the state. And why we do this? Because every single euro that the government put in ESA, the European Space Agency, the economy of the country takes back 3 euros. So why? Because we are putting the money there, and they will go to the industry, they will go to the most qualified people, and buy them, the most technological instruments that we have in our planet. Otherwise, it won't be able to we won't need this technology for anything else, because just imagine the biggest instrument and the most expensive instrument that we have in the world is the particle accelerator Atlas in CERN, Switzerland, and this is the biggest instrument. And to make that instrument, we spent millions and millions of euros. That was made by companies that are very highly technology companies. So this is a way for the governments, and the governments very usually use astronomy and space explorations to finance industry. It's since they are not able to go and give money to the industry and to the private sector, they do this in this way. This is also what is happening in America, and President Trump realized this, because if we are able to create a branch of the army that is in space, he will. I don't think he cares about protecting the space, because there are not too many weapons in space, but he will be able to finance the private sector with this. You will be able to put billions and billions of dollars in the private sector. Of course, all of this came with the motivations that we want to do things. And if we want to do these things for the mankind and for exploration and to know more and more and more, we should do in the way that European countries are doing it, because the possibilities that we are open to the academic community are so higher. Because just imagine a telescope that is in Chile that belongs to the ESO, European Southern Observatory. If you want to get 1 night of observation, you need to apply. You need to apply for this time in this telescope. You need to ask, and you will be competing with so many scientists in the world, because this is the top instruments in the world. And what will happen, that astronomers realize, is that they need to create consortium. I was part of one that we were trying to reach time for this instrument that we can see in this image. We were applying time for this, and I can tell you, this instrument will only be done. It's not done yet. It's being built. It will only be in 2024. So, and we are already applying for time in this. The name of it is ELT, extremely large telescope, and you can see the size is really, really big. It will be the biggest telescope in the world. And it was my job to do an observational strategy for this telescope. When we have the time to do it, we already have the observational strategy. This was one thing, that to apply for this time, we needed to do the observational strategy beforehand. This we call to this the case studies of the telescope. We try to see what we will discover when we have the time to observe. And this was done a few years ago, and the telescope still not built. But yeah, the science community already start working with it, already start finding new things in the universe. And the bigger one that we have right now is this one, that is here, that is the VLT, the very large telescope, that is also in Chile and also belongs to the European Southern Observatory. This is 4 units of telescopes, and these 4 units can work together. This is important to understand what happened with the image of the black hole. So these 4 units can work together with a method that is called interferometry. That is, these white lines that you see here, the light came from the telescope, will follow this path, and then it will be focused here at the same time, the light of the 4 telescopes. So the 4 telescopes will work as one telescope, one as the bigger one in the world. So this is what interferometry means. This technology that can combine 4 small telescopes and turn it in one big, huge telescope. And this is also what was done with the Event Horizon telescope, but this is in a different dimension, because it was used these 4 here. this is a radio telescope. It's not a telescope from the visible. It's a radio telescope. It's like an antenna that we point out to the sky, but we can see that image that we saw with these antennas, and as you can see, these 4 units around the world. And we are working here with this is a network of radio telescope, and we use a very long baseline interferometry. That is the name of this technology, that we can use things in different places in the world to observe. This was also the telescopes that observe, some of these, not all of them, that observed the gravitational waves a few months ago. So how is this important for us? This is important, just one reason it will be enough, but this is like, the more we know, we understand that we don't know that much. And when we are observing the black hole, that amazing picture of this black hole, what we can realize, because we can take much more than this, the scientists can have much more than this, than just a simple image. We can realize what is this, we can realize what is happening around the black hole. We will understand that maybe we knew less than we thought. So, and this is happening in all the science. When we are trying to figure out more and more stuff, we understand that we know less than we thought. This happens in students when they are in school. The ones that came from an exam saying that it went very well is the ones that know less, because they don't have a very good view of the entire knowledge. And this is important for the mankind, to have a view of the entire knowledge, because this small image of this black hole is not with a great quality, will help us to understand what we need from our future instruments. So we will adapt the technology from now on, from the day that we discover this, the technology will be adapted so we can observe better and better these objects in the space. So this is one thing. And the other thing is, of course, the economic return that we can have from these investments in space. And the other thing is even more obvious, but sometimes we didn't know. We don't know, but even the small photographic machine that we have in our phones, the microwave in our home, everything came from space exploration. Things were discovered first to be used in space. This technology was developed to be used in space, and then we use this technology in our daily life. So this is the way that can change our worldview. But it can change also, not in a negative way, but in a different way. Because when we understand how big our universe is, when we understand how difficult to live outside our planet is, we will understand that we need to cherish our planet. We will need to take care of our planet, because it's impossible for us right now to live in the South Pole. It's impossible for the mankind to live without a lot of technology there. Just imagine, we cannot go just there and live in the moon. We cannot go just and live in Mars. We will really need to cherish our planet. We will really need to have to take a better care of our planet, because we didn't find yet a planet similar to ours. If we find it, it will be light years away from us, really, really far away, that we were never able to travel that far. For example, this black hole, let me go back to the black hole image, just for you to know. The distance from here to here is bigger than the solar system. This distance is bigger than a solar system. So this distance is bigger than what we were able to travel until now. We were not able to put a machine outside the solar system. So we can see how difficult it will be for us to work in our universe. We cannot travel outside our solar system. just with this image, just collecting the light. But basically, this is the black hole coming to us. It's the light that are coming from there to us. It's not us going there. So this is one of our reasons that this technology, these views that we have of space should mean that we need to take care of our planet first. We need to find a way to improve the technology. We will need to find a way to be able to live here in peace and with the resources that we have, because using the resource of all other planets, using the resources of our other solar systems or other galaxies, it's something that is hundreds years from now. So, and I think I finished. This is just a small bibliography that I put it here. If you want to read something more mathematical with a lot of formulas, you should find this one. But this one is for people that has a physics background. If you don't have it, you can use this one with high school mathematics and high school physics. It's also a very good book to understand a little bit. But of course, if you don't have any background, any knowledge about physics, this is the ideal book for everybody. A brief history of time from Stephen Hawking. And that's it. Thank you very much. I'm looking forward for your questions, and I hope I interested you in this topic and you enjoy it. Thank you very much.
Well, thank you so much, Pedro. This is a wonderful presentation on black holes and on the region in space where the density is so high that it creates a gravitational field so strong that nothing can escape it, including particles of light and everything else that there is. I want to invite our participants to use the question and answer box at the bottom of your Zoom application to post some questions for Pedro. You can also make comments in the chat area if you would like to share your comments with all participants. I had a question, Pedro, as you were talking, and I realized I don't know too much about astrophysics and what's going on outside of, probably what's going on outside of this room that I'm in. But anyway, my question has to do with, is there something opposite to the black hole? So the black hole sucks everything in due to gravity, but is there something that expels everything? What force would that be?
Yeah, that is a theory that, of course, as like other theories, we are not sure about it. But is the white hole, for example, a white place where the light, where everything that went in a black hole will come out. And there are a few theories that believe in this, that what happened will come out in other points of universe. That is a white hole. That is the opposite, and it's a place where everything comes out from the black hole. But we need to keep this in mind, because as many matter the black hole aggregates, it gets bigger. So it means that the matter is staying inside. See, the matter is staying there. So this is something that we need to think about it, but it really means that the matter is going anywhere. In the other side, we don't know. But it means that if it gets bigger, something must stay there. So
yeah, interesting, very interesting. Well, okay, there is a question here in the question and answer box. I want to just move on to that. And from, I don't have a name, but the person is known as meeting manager, says, Obrigado, Pedro. Given that the UN Intergovernmental Panel on Climate Change projects that we have 11 years left to take significant action on this human-created crisis, I am wondering how this knowledge you have about astronomy and black holes will support our taking effective action to meet this challenge. Is it just a question of cherishing our planet, as you say? Wouldn't the billions being spent on European Union programs to support astronomical research be better spent on sequestering carbon from the atmosphere, making use of the microbiome capacity of the soil in regenerative agriculture, while also producing food and conserving water? This came from our friend Leora Adler. Thank you, Leora.
That is a great point. When I say cherish our planet is to, I don't want it to get too much into the ecological and to preserve our planet point of view. But when I say this, is like the mankind, the humanity to go and travel to other planets. That will be impossible for the next years. But this using the astronomic, using the space to work with us, in our planet, that is totally possible. That will be possible in the next, I don't know, 11 years, but 20, 30 years, that will be possible. That we will use the space around us, we will use the at least maybe the moon, so we can have a better life here, so we can preserve our planet. And that should be the investment. How we can use space to make sure that our life in Earth is that, to make sure that we are able to live here in our planet. This should be a holistic relationship, a very close relationship between space and our planet. Not to think as space as the next place to go, but to think as the next place so we can collaborate with.
Excellent. Some people put questions in the chat box, and that's okay. We were hoping to have more questions in the question and answer. It's a little bit more orderly, but in any case, Alvaro says our solar system moves in a certain speed that affects time, and so the same about gravity. Which one affects more our perspective of time? Interesting question.
Yeah, and this is a question about the special relativity. That what we know is both of them. We have this perspective of time when we are working with two different referential. Since the entire mankind is inside our planet, it's inside the same referential. That is the solar system moving around us, the planets moving around the sun. So this is the only perspective of time that we have. But if we are able to put one person, two person, atomic clock outside this system, then we will know, we will understand what is the relation with these two perspectives of times. But this has only to be, the relation with this is only about this, the referential that we are, where we are. What is the origin of our referential? And right now, the origin is our planet. So since we are moving like this, we are inside of the train, seeing the trees passing by us outside. So, and this means that we don't have anything outside of the train. We are just us right now. To be able to understand what is the relation between what is outside of the train and inside, we need to put someone outside of the train. And we are not able to do it. We are not able to understand it yet.
Very interesting. And I'm sure Einstein struggled with that for quite a while. So Sarah says that when matter enters a black hole, is there a limit to how condensed the atoms can become? At the center of the black hole, is there a solid core that is fixed? Or does the matter just keep getting denser and denser?
Yeah, that's why it's called a singularity, because the density is so high that will create a higher density. And what will happen, and it's happening in black holes, is this. We are creating more and more density. And since we are creating more density, the black hole, the event horizon is expanding. The black hole is becoming bigger. So what I can say is there is no limit. There is no limit. Everything is going there. The atoms will get in higher temperatures. The atoms, this is also happening inside of our sun. This is also happening inside. I didn't told you, maybe I forgot, but there is two kinds of black holes. The black holes inside the galaxy that are supermassive black holes, and the black holes that came from the dead of stars. And these black holes that came from the dead of stars, it's when the density of the nucleus of the star are so high that it will create a black hole. And this is where everything starts. And since what is happening inside the, I will draw, sorry, because sometimes it's easier to draw. So we have a star with hydrogen, a lot of hydrogen. And what will happen inside the star, because we have this pressure of the everything, the temperature here will get higher. So this hydrogen will become helium, will become a heavier metal. So we will still have hydrogen here. And the helium, since it is a heavier metal, what will happen is it will increase this pressure. This pressure, not this pressure, but the gravity, everything that is pulling matter to the nucleus of the star will get higher and higher. So this helium, by nuclear fusion, will become carbon, oxygen, and other metals, for example, another metal. So these metals are heavier and heavier. So what will happen is that we will have a nucleus of a star so dense, but so dense, that the rest of the star will create here a void between the nucleus and the rest of the star, and the rest will go to the space. And here we will, since we have such a high gravity, such a huge density, we will create a black hole. This is normally what happens to very heavy stars heavier than the sun. Stars like the sun form a planetarium nebula, and this planetarium nebula is the same effect, but here the density is not that big. So the density inside will create a white dwarf star with a lot of carbon. But when the star is bigger, so it's able to produce more matter, more heavy metals here, this will become a black hole. This is a stellar black hole. And these stellar black holes will increase. But what's happening is maybe there is a limit for what we can put in the simple place. But we don't know it, because what's happening is the events of horizons will get bigger. And if we have more matter in, the events of horizon will get bigger and bigger. And what's happening here, we don't know. If there is the theory that everything will go out in some places, so that we can say that it can get all the matter that he wants, the black hole. But even if it does, if it doesn't, even if everything stays here, we don't know it, because we never got in. And it's very difficult for us to predict what is happening inside the black hole. So we know what is happening here in the event horizon. We know that there are some particles around here that irradiate some radiation. So we know this. The radiation of Hawking says that if a black hole doesn't get bigger, it will get smaller. It will lose matter. This is what Stephen Hawking said, the Hawking radiation. This means that the particles and the pairs of particles and antiparticles around here will get loose, will get off the black hole. So this we know, that when they get more mass, they will get bigger. And if they are not getting mass, they will get smaller. So, but we don't know how many mass it can retain, but I believe it's unlimited.
Wow. Quite amazing, quite amazing. Well, I don't see any more questions coming up, Pedro. I think we're also getting close to the time allotted for this webinar. We don't want to make it too long, but I want to remind people that it will be recorded. It has been recorded and will be available in our YouTube channels. Just to conclude, let me just say that, yes, well, thank you, Pedro. There's so much that we don't know, and we live in this universe with so many things affecting our lives every day. Black holes are some of the least understood, I think, phenomenons in our universe, but it does certainly affect our lives and things here on Earth. And as you pointed out, it also emphasizes the need to take care of the planet that we are living in, and to make sure that it's following its natural state, its natural trend, as it would, if it would be. So again, thank you so much for this, Pedro, for your inspiring presentation. Thank you to all the participants. I want to remind everyone of some of our other Gaia Education programs, such as our learning journey that leads to a Gaia Education certified trainer after taking some face-to-face, two of our face-to-face courses and at least one online course to deepen your knowledge. Please look at that in our websites. And also, the next webinar is going to be presented by our friend and also one of our course facilitators, George Mello. That webinar will be in Portuguese on May 15th, and it will be also about the personal relationship to how we integrate our worldview into our lives. Gaia Education next online course is the Worldview, precisely, and this is why we're presenting this today. So on May 20th, we'll begin the online English portion of the Worldview design. And on May 27th, the same course will start in Spanish. So come to our online website and register now. You can actually get a 20% discount for early bird registrations. You can also take advantage of this 10% discount on our products, such as the eco-villages around the world, the 4 keys. These are publications that Gaia Education makes available to our general public, and the sustainable development flashcards to initiate conversations in your communities about sustainable development and joining the movement that the UN has started around sustainable development. There is also a multiplier handbook that can help you step by step in those conversations. Subscribe to our newsletter and get a lot more information about Gaia Education. Thank you for being with us today and hope to see you. Please come to and register to all our webinars. We have a whole series. We're trying to run a webinar once a month. So please come to our web pages and register for the whole series of webinars. Thanks again, Pedro. Thank you, everybody.
Thank you very much.
Okay, I can stop the recording.